Bonjour à toutes et à tous. Merci pour votre présence et disponibilité. Aujourd'hui, on a l'honneur et la chance d'avoir parmi nous le professeur André Becker, qui est un collègue avec qui on travaille depuis à peu près maintenant 5 ans sur le chantier Gabon, que vous connaissez peut-être un petit peu. Et donc, André, professeur à l'université du... C'est un Américain, professeur à l'université du Manitoba au Canada. Et donc aujourd'hui, il est parmi nous dans le cadre de collaboration, en professeur invité à l'université de Poitiers. Il sera là pour une période assez limitée maintenant, mais il reviendra printemps prochain pour rester 2 mois. Et donc André aujourd'hui va nous présenter ses travaux de recherche, au moins un résumé de ses travaux de recherche sur tout ce qui est lié à l'histoire de l'oxygène dans l'atmosphère de la planète. Et comme vous le savez tous, on a, sur une période assez particulière, entre l'Archéen et le Paléoprotérozoïque, donc entre 3 milliards et quelques jusqu'à à peu près 2 milliards, notre planète a connu des périodes assez cruciales dans l'évolution de l'oxygène dans son atmosphère. Et ces changements ont impacté très probablement la géosphère et la biosphère. Et donc, André est parmi rares personnes dans le monde qui a eu l'occasion et l'opportunité de visiter plusieurs endroits, un petit peu partout sur notre planète, où on voit ces affleurements-là de cet âge-là. Donc, c'est pour ça qu'aujourd'hui, on va essayer de bénéficier, profiter de son expérience et essayer de comprendre un petit peu ce qui se passe sur l'histoire de l'oxygène au niveau de notre planète à cette période-là. Donc voilà, je laisse la parole à André, et bien sûr, à la fin de l'exposé, vous avez tout à fait toutes et tous le droit de lui poser les questions que vous souhaitez. Alors, c'est en anglais, je pense que ça posera problème à personne, mais si jamais il y a un souci votre question est en français et vous souhaitez vraiment la poser, dites-le nous, et puis nous, on va la traduire sans problème. Mais j'imagine que vous êtes parfaitement bilingue, je n'ai aucun souci avec ça. Merci André, thank you very much for your visit, and we are very honored to have you here, and à vous.
Thanks Abder for invitation, and I have to, I'll talk in English, but I'll try to talk slow, and if you have questions, feel free to stop me, and I will try to go in more details if you ask. Okay, so what we talk about, we'll talk about evolution of atmospheric oxygen for a time. And so there are a number of different models, and first I want to introduce why do we care about evolution of atmospheric oxygen in time. Well, we don't have lack of oxygen in atmosphere, only maybe in Japan potentially there is a growing need for oxygen. So why do we need to worry about what was atmospheric oxygen in the past? The reason is because oxygen is connected to a number of other parts of Earth system. If we think about evolution of life, generally it's envisioned that were very simple organisms very early on, like cyanobacteria, making microbial meds or making stromatolites, and later on, at the end of Precambrian, around 600, 560 million years ago, when first animals evolved. So if evolution of atmospheric oxygen was different, could it create opportunities for animals or for more complex organisms to evolve early on and then to disappear later on? And if that would happen, would it show us that evolution proceed in a repetitive pattern, so there is only a single pathway for life evolution, or there are multiple pathways, and Some of them were explored early on and discontinued and never were followed later on. So that's one reason it is connection between life and atmospheric oxygen. Another reason is connection with climate. So in modern atmosphere, carbon dioxide serves as a major greenhouse gas. But if we turn our attention to early time in Earth history, atmosphere was anoxic. And in an anoxic atmosphere, different gases could have played a major role as a greenhouse gases. So for example, methane. Methane is not stable in modern atmosphere. It would exist only for residence time would be only 11 years. But in oxic atmosphere, it would be stable for much longer. And methane is a much more efficient greenhouse gas compared to carbon dioxide. So potentially in the early times were different components contributed to stability of the climate. And as oxygen increased in atmosphere, they would disappear. And it would be marked by major climatical changes such as glaciations. So that's another implication of study of atmospheric oxygen. And so with this in mind, let's think about like what do we know about evolution of atmospheric oxygen. So generally, as in Europe, like majority of people study Phanerozoic. So we know a lot about Phanerozoic, evolution of life in Phanerozoic, deposition of sedimentary rocks or processes. When we go in Precambrian, a number of people, especially in the past, was much smaller working on Precambrian because age constraints are not good. It's immense amount of time. So we're talking about time which probably 5, probably even 8 times duration of the Phanerozoic. So it's large amount of time. And when you're trying to compare processes on different continents, it's complicated because we don't have a very good age resolution. So as a scientist, what we tend to do, we are trying to connect dots, right? So we make one observation at a certain time in Earth history, and we make another observation in different time in Earth history. And when we're trying to connect this observation, assuming linear trend between these two observations, which is not necessarily have to be true, but it's a satisfying kind of assumption which allow us to reconstruct some trend in Earth history. So when we look on evolution of Earth components, like for example life, we for a number of years we were perceiving it in a linear progression from simple organism to complex organism. If we look on atmospheric oxygen, and as you can see diagrams here, we generally see it in a stepwise fashion, like increase in atmospheric oxygen between 2.5 to 2 billion years, and then stability, and then sort of another increase later on, or like shown here. In one increase, and then another increase, and then little changes in Phanerozoic. And by the way, take a look like how minor these changes in atmospheric oxygen in Phanerozoic compared to this major jump that happened between 2.5 and 2 billion years ago. Or in terms of climate evolution, in terms of concentration of greenhouse gases, we also look on it in a linear fashion. And now with development of better geochronological constraints for Precambrian, and now with better correlation between different continents and in the world, we can actually see that this picture is probably simplistic. I mean, why should we expect it to be simplistic? Because if you look on Phanerozoic, what do you see? Oxygen went up and down and up and down in response to changes in environments. So there is no reason why it wouldn't be a case in Precambrian. It just satisfying kind of simplification that allow us to present it in a simple way. So to get started, here's a generally accepted view as 2008, that oxygen increased around 2.3 billion years, stabilized for a long time, and increased again at the end of Precambrian, leading to appearance of animals and life as it looks similar to us. Earlier on, as you can see, were some arguments where people sort of one camp of group, which is leading, would put increase of oxygen somewhere in early Proterozoic, and then stabilization at later time. Or other group led by Amota would argue from early on was plenty of oxygen in atmosphere. So this group by Amota is relatively minor. Most people agree that was very little oxygen early on in Earth history, and when it's increased in early Proterozoic. So what I will be talking here is based on collaboration with a number of people, and I should acknowledge that it's a large group of people involved, and I probably should have, I will not show pictures from up there, but I should have probably added up there here, because one of the components of this study is understanding how life evolved through time. Okay, so what I will talk about today, I will try to introduce you geological and geochemical evolution of Paleoproterozoic surface environments. And it's, as you can imagine, a pretty big topic. And I will focus mainly on the rise of atmospheric oxygen and climate changes, carbon isotope variation in seawater composition, and sulfide evaporites and phosphorates. And you can ask, like, why did I choose these topics, and what is connecting these topics? I hope I will be able to explain it to you, but basically atmospheric oxygen effect on composition of greenhouse gases and climate changes, and carbon isotope cycling in surface environment influence release and consumption of oxygen in surface environments. Sulfide evaporites will reflect level of sulfide in seawater, and in that sense oxidation state of seawater. And phosphorus is a major nutrient for life, and so this redox reaction would likely be linked with presence of nutrients in the ocean. So I hope these connections will become more obvious as we go through the talk. So I will sort of discuss present constraint for the rise of oxygen in terms of age and in terms of geochemical evidence for it. And then I will present sort of this model that oxygen could have gone very high, and we don't know really how high, in early Paleoproterozoic, and when it sort of went down and stabilized at low level, and it was sort of at relatively low level until the other end of the Proterozoic, where it again went up, allowing sort of complex life to evolve. So how do we know that oxygen was lower in the past? Like, I mean, it's a nice idea, but as a geologist, we want to see some evidence for it. So if we go to earlier rocks, to Archean rocks, what do we find there that tells us that atmospheric oxygen was low? And what is different from modern environments, that we go to conglomerates, to sandstones, and we find this sort of rounded grains, and if we analyze them, we find that they're uraninite. And uraninite would not be stable at the surface of the modern Earth on a relatively long geological timescale. It would get oxidized, and uranium would travel in solution. So why it didn't happen at early times in Earth history? So some people would say, well, it's because you didn't give enough time for uraninite to get oxidized. It was very quickly buried and eroded from mountains, quickly buried, and didn't have enough time to react with oxygen. As a sedimentologist, you can respond to it, well, if we look on the sedimentary succession, do we see evidence that they are mature, that they deposited slowly, or do we see evidence for this very fast sedimentation rate? And we find this conglomerate sandstones on passive continental margin, where sedimentation rate was slow, where basically grains were slowly moving up and down by tides and have plenty of time to interact with atmospheric oxygen, and yet we find this uraninite around it, so it has plenty of time to move around and get rounded by wave action, and yet not reacting with oxygen. With more studies, people even found that pebbles of siderite. So you can see here layering, and it's truncated because it was a pebble, and it's overgrown by new siderite. And so this, again, siderite would not be stable in modern rivers. Like if you would put it in a river in France and let it sort of travel to the ocean, it would never get to the ocean because it would get oxidized and converted to iron oxides and kind of disappear. We find this conglomerates made of rounded, beautiful, so-called bucket-shot pebbles of pyrite. Again, pyrite would not be stable in modern atmosphere. Like if you go to sort of deposits of sulfides, yes, you see where pyrite, but you go along the waste for 1 to 10 kilometers, and suddenly pyrite disappear, and oxidation of this pyrite led to sort of contamination to environments, and people talk about this arsenic pollution, or all kind of processes. Another rock that we don't often see in modern record is banded iron formation. So basically, massive deposition of tens and hundreds of meters thick layers of iron oxides. To transport iron oxide in solution, it has to be in reduced form, in iron 2+ form. In iron 3+ form, it would be deposited, it would not stay in solution. So presence of these banded iron formations indicate that the deep ocean at that time, where this iron was released, was not in oxic state. So iron was traveled in an oxic state until somehow it was oxidized and precipitated as iron oxyhydroxides. And when we arrive in Earth history at the time around 2.4, 2.3 billion years, and suddenly things change. We start to see what happened at that time. We find glacial deposits on different continents. So you can go to northern part of Europe, to Finland, to northern part of Russia, and or you can go to Canada, or Australia, or South Africa, and in the deposits with age between 2.5, 2.3 billion years, you find this finely laminated mudstones, argillites, and sort of the fine laminations, and in them you find this what we call drop stones, basically an explanation for it that sort of iceberg was floating on water, and as it was melting, it was dropping the stones for watercolor into the finely laminated sediments because we were below wave base, maybe even below storm wave base, so they were finely laminated, except this big boulders were coming sort of on the top of them. So you wouldn't want to be a small microbe living on the surface of this finely laminated sediments with this sort of boulder size of my head or even larger coming on top of you. And what else is interesting at that time? You go to deposits overlying these glacial deposits, and you find they full of this pseudomorphs of crystals, which are after sulfates, after anhydrite or gypsum, and that's something you don't find at all in Archean. If you find sulfides in Archean, they would be barytes, and they would be formed around hydrothermal vents. But this is shallow water deposits, like in the tidal zone, and they full of this remnants of sulfide evaporites. So what is required to increase sulfide concentration in the ocean? It requires to oxidize pyrite on the continent and to deliver sulfide in the ocean, and for ocean to be largely oxic, because if ocean is anoxic, it would be reduced to form pyrite. All sulfur would go into pyrite. So to allow rise of sulfide in the ocean, it requires two conditions: oxidative continental weathering and oxic ocean. And so we go to different continents, to different sedimentary succession, and we find this sort of sulfide evaporites. And finally, straight above these deposits, we find this finely laminated red-colored first red beds. Like red beds practically are not known in Archean succession unless they were exposed to recent or modern weathering. And so basically it would be not ancient phenomenon, it would be modern or recent phenomenon. But if you go into a succession starting with 2.3, 2.4, red beds become very common. And so it's a question like that we didn't hear with Gabon, like we find these red beds, they are well developed, are they primary or sort of are they secondary? So it's a question that some students here probably will be answering. So was this dramatic change, to summarize, in oxidation state of surface environments, and in association with this change was the Paleoproterozoic glacials, major ice ages, or if you're familiar with Neoproterozoic history, so-called snowball Earth events that occur at that time in North America, West Australia, South Africa, Europe. They all, in terms of age, relatively poorly dated, so they are younger than 2.45 and older than 2.22. And the only age constraint within this 230 million years is Rhenium-Osmium age in South Africa. So the reason why we're lacking age constraint within this group, because magmatic events were relatively rare within this 230 million years. Like there are major mafic dikes, intrusions, volcanism at 2.45. 2.22 event is very common through Earth. You can find mafic dikes from Canada to India to, I don't know about Brazil, but probably if I look, would be went there. But between these two ages is not much happening. And that makes our life very complicated, because We kind of 230 million years for Phanerozoic. It's a huge amount of time. And so if you would start correlating something in Phanerozoic, dealing on a time scale of 230 million years, people would start laughing about you. You need to improve your age constraints. And so that's something I will present here. Okay, and so in terms of rock record, what are most critical succession for this time intervals? And I'm talking about this time between 2.5 and 2.22. So two most well-studied successions are in Canada, Huronian supergroup, and in Southwest Africa, Transvaal. And so what I will be presenting here, and it might be somewhat confusing for you if you are not familiar with stratigraphy of these two areas. But what we are trying to do, sort of to use various tools like chemostratigraphy, geochronology, and to correlate with two successions on two different continents now, because what we want at the end, we want to see a progression in time, how through Earth history, through this time intervals, things were changing. And because rock record is fragmental, we need to go to different continents. We need to assemble information from different continents and transfer it into some diagram where on a horizontal axis we will have time, and on vertical axis some changes happen. Okay, so I mentioned phosphorites, like how phosphorites fits to this picture. Like you go into Archean record and you don't find phosphorites. Like yes, you find small apatite grains here and there, but if you would be economic geologist and you would offer your company to start mining for phosphorus in Archean, probably you would not make a lot of money. Maybe you would lose a job. So why should be any connection between phosphorus and appearance of oxygen? Like phosphorus is not really a redox sensitive element, so should be no connections. To emphasize it, here's a sedimentary succession in India. It's not very well dated, but we suspect it's around 2.1, 2.2 billion years ago. And it's full of this columnar stromatolites. So this phosphorites making stromatolite columns. And they are not something like exotic thing to look and to admire, but they're actually something that led to opening a pit like 10 or several tens of kilometers wide, where people are mining these phosphorites with 2.1, 2 billion years age and making decent money on it. So why should phosphorites become more abundant in this time? So that should be some connection to the oxygen, and we will try to discuss it at the end of the talk. Okay, so what else happened at that time? So we talked about glacials, we talked about oxygen appearance. What else is sort of unusual at that time is that carbon